In this lesson, we're learning about the tree of optimal value. A tree is a connected graph with no simple circuits. Remember, a simple circuit is when you start at one vertex, follow a path, and return to the same vertex without repeating any edges. Here's an example. This is a tree. As you can see, there's no way you can start at one place and return to the same place without backtracking. This graph, however, is not a tree. You can see that you can very easily run a circuit here without having to backtrack. Here's another example of a tree. Again, you can see there's no way you're going to be able to do a path because you can never loop around and return to the same place you started without backtracking. Same thing here. We have a graph that isn't connected. A and B is not connected to edge CD. There is no simple circuit there either. In the first one, there was a tree. Second graph, it was not a tree because there was a simple circuit. Third one, also a tree. And fourth one, not a tree. A tree of optimal value selects only some edges in a graph such that all vertices are connected. There are no simple circuits, and we use either the largest or the smallest weighted edges, depending on whether we're trying to find an optimal value that maximizes or minimizes the weighted edges. There are several steps to creating a tree of optimal value. If we're looking for a tree of minimum value, we copy the vertices of the graph, select the edge with the lowest value and draw it, and then of the remaining edges, we select the one with the lowest value and draw it. Then we keep selecting the smallest edge and drawing it, unless an edge will create a simple circuit. If it creates a simple circuit, then we skip that edge and move to the next one. Once you've created a tree, stop drawing edges. To create a tree of maximum value, follow the steps above, but use the edges with the largest value. Here we're asked to create a tree of minimum value given the graph below. Our first step is to identify the edge with the smallest weight. In this case, it's from F to C. Then find the next smallest, from E to D. Next smallest is from D to C, and after that it's F to E. However, by putting in F to E, that creates a circuit. We can now go around this way. So in that case, the rule tells us to skip that edge and go on to the next smallest one, which in this case would be F to B. Continuing to the next smallest, F to A is 10, and now we can see we've completed the tree. We've connected every vertex with edges, and we started with the smallest one and added accordingly. This gives us the tree of minimum value. Try this question, and then come back and see if you've got the solution correct. A hydroelectric dam generates electricity, which is transmitted using high-tension lines to Quebec's main urban centers. These transmission lines lose some of their power as the electricity is being transmitted. The graph below shows some of these lines and the power loss in tens of megawatts. Vertex H is the hydroelectric dam. The facility's engineering crew wants to minimize the power loss while connecting all urban centers. Which high-tension lines should be used, and what is the total loss? The first key message we've got here is that they're trying to minimize power loss, so we know we're going to start working with the edges that have the smallest weight associated with them. We start by duplicating the vertices of the graph. Once we've done that, we look at the original graph and find which edge has the smallest weight. In this case, we've got S and Q is 3, but we see that H and F is a weight of 2. So we'll draw in that edge and add its weight. Next, it looks like S to Q is the next smallest. I also notice that we've got R to A, which is also 3. We'll draw in that edge. Next smallest, R4, where we've got R to S, F to C, and A to M. They're all 4. So I'll start drawing those in. Next on the list is 5. So I can go from S to F. Now alternatively, I could have added in Q to C and not put in S to F. Both of them are weighted with 5, and they both accomplish the same objective of giving us a tree without creating a circuit. We can see at this point now that we've completed the tree. We've connected every vertex, starting with the smallest weights and increasing until we had them all connected. A city park has developed a series of trails between various parking areas. In the winter, the city wants to maintain the fewest number of trails such that all parking areas are still connected, either directly or indirectly, but the total trail distance is maximized. The graph below represents the parking areas, or the vertices, and trails, are the edges, where the weight of each edge represents the length in kilometers of that trail. Which paths should the city maintain in the winter, and what's the total distance of trails available? For this problem, we're being asked to maximize the distance. As a result, we're going to start by duplicating the graph and starting with the largest edges this time. I've got the vertices in place. Now let's go looking for the largest edges. The first edge that I see that's largest is A to D. I'll add that to the graph. Next largest looks like F to A, with a weight of 8. After that, we've got two paths that have a weight of 7, F to D and A to C. If I add in F to D, however, I'm creating a circuit, so F to D will not be included in the graph. However, A to C does not create a circuit, so we'll add it. The next largest is F to E, and after that we want the largest connection that'll bring in the last vertex, which in this case, for A to B, is a weight of 2. Finally, it asks us what is the total distance of trails available. All we have to do is add up all the numbers. 5 plus 8 is 13, plus 2 is 15, plus 10 is 25, plus 7 is 32. Try the practice questions, and then come back to watch the video of the solutions.